Okay, first speaker is Dr. Theodoros Horikis. He will talk about light meets water in non-local media. Okay, please go ahead.
Again, thank you for the invitation. It's a great pleasure to see Kenichi and meet Murasige for the first time. So I want to talk to you about what the title basically says. It's what you're going to see. What you're seeing here on the left is you see numerical simulation of what you will see later to be a non-local model exhibiting solutions that we find in shallow water, and in particular in two-dimensional shallow water, as these are described by the KP system, the KP equation. So this work is done in collaboration with Dimitris Prozaskakis from the University of Athens. And let me, a small summary before we start. What you're going to see here is what we think are very interesting solutions, new solutions that you can find in the small amplitude approximation of an NLS type equation described by a non-local system. And you can find these systems that you see later in nematic liquid crystals and so on. But what you're going to see is that what I said in the beginning, you're going to see shallow water wave solutions, okay, in exhibited in or described by the KP system in light. So what's really exciting, I think, is that you can see, even in the small amplitude approximation, you can see where the two meet. In what way? There is a small trick that you will see later, that a small parameter can define everything with respect to the solutions. I'll tell you more in a second. I did forget to mention that the photos that you saw in the beginning are in a paper by Ablovich and Baldwin in Physrev E. So when you talk about nonlinear optics, the first thing that comes to mind, of course, is the nonlinear Schrödinger equation, which you see on the left or on the right, the same system. What you see here is the envelope approximation of the electric field under the paraxial approximation. Forget about that. That's a bit of physics. If you're interested, I can tell you more about the physics, but we don't care about that for now. We only care about the equation on the right, which we call the nonlinear Schrödinger equation, the NLS. And what's important here, the half in front of the linear term doesn't mean anything. You can trivially forget about that. The half is not important. What's important is the relative sign between the linear part and the nonlinear part. So when you have two pluses, you call that the focusing case, or you have a plus and a minus, you call that the defocusing case. So these are two distinct equations, two different equations exhibiting two different solutions if you want to solve them in, say, 1D. Okay, so the start is nonlinear optics and the NLS. Fine. So why do you want to go to what we'll see to be a non-local system? Well, a non-local system can appear in many applications. The NLS is, of course, an approximation to some extent, but you can find other approximations better suited to describe thermal media, atomic vapors, nematic liquid crystals. I'm very interested in nematic liquid crystals. It's a work we're doing with Noel Smythe from Edinburgh, and of course, BECs. So there's a plethora of applications that you find that the NLS is not a good approximation to describe these phenomena. So the focus here is this system, as you see it here. Okay, now we have the evolution in time, as you see, and then the delta denotes the Laplacian, as you would expect, and I have it here in both Cartesian and cylindrical coordinates. Okay, so we're going to see different solutions for different geometries, essentially. Okay, so you have the Laplacian for the Cartesian geometry, and then you have the Laplacian the transverse Laplacian, of course, for the cylindrical geometry, okay? So different geometries, of course, imply different solutions, okay? And you'll see how these appear distinctively. What's important here to see is that the second equation can be reduced to the NLS. If you take d to be 0, the second equation becomes now, it's essentially trivial to see that n is nu squared. So this, the system uncouples, and you have the NLS, but you have the defocusing NLS because you have a plus and a minus, okay? So again, applications, I mentioned some applications before. What's important here is to see that it's very difficult to construct exact solutions of that system. To some extent, I'm arrogant enough to say that you don't care even to construct exact solutions in terms of solitons or in terms of bright or dark solitons as such, okay? What's interesting here, and I have some citations here if you're interested in some of the properties of the system. What's interesting here is that you can have you can use the solutions of another system, in a sense, tricking the non-local equation into believing that it's a KP system, which I think is very interesting. So you can exhibit KP properties under NLS in the small approximation. Let me tell you how that's going to work. So we start from the non-local NLS. You start from the non-local NLS and you do asymptotics. We're under the small amplitude approximation, and we use multiple scales. So this is a two-step process, as you would expect from water waves as well. If you go to the water wave problem, you start from the Euler system and you have a two-step procedure. First, you derive the Boussinesq equations, okay? And then under long time asymptotics, you get the KdV, or in our case, because it's a 2D problem, you get the KP equations. It's exactly what we're going to do here as well, okay? And you can do this in water waves. Matteo should be very interested in plasmas, because one of the systems that and I'm very interested as well lately, is a system that it's very close to the intermediate asymptotics that I'm describing here, okay? So we start, of course, using the Mandel transformations that you see. What is U naught here? U naught is essentially, it's going to be a constant. You'll see that this is essentially a background on top of which our solutions are going to live. So U naught is a background. And then, of course, this is amplitude and phase. You substitute back to the NLS, separate real and imaginary parts, and this is what you get. This is trivial. I haven't done nothing here. Just substituted, separate real and imaginary parts. Okay. First solution is the trivial solution. Of course, you find the time-dependent, only time-dependent solution, which is this one. We like to call this the continuous wave solution. Okay. Normally, in the context of the NLS, you would call this the background solution. It's the continuous wave. If you're talking about gray solitons, for example, this would be the boundary conditions, and then the dip would be your dark soliton. Okay. What's important here is to look at the properties and stability properties of that solution. You see, if you're going to construct your solutions based on that background, on this background, well, you better make sure that this background is stable. Because if it's unstable, any small perturbation, and a small perturbation is going to be my solutions that I'm going to be adding to that background, will make it collapse. So I'm very interested in making this background stable, okay? And if you want to make that background stable, you see that my dispersion relation is at the bottom. This background, if D is positive, the non-local parameter is positive, everything is positive, I have no problem. This is a stable solution, period. This is a modulationally stable solution. There's no doubt about that, okay? But this is crucial. You have to pay attention to the stability properties of your background, okay? And this is what I meant by why the stability is important. Look at the second equation for rho. You see rho now, because I've extracted U naught, rho is 1 plus a small perturbation. Well, guess what? If that solution is not stable, then 1 plus a small perturbation to that background will make it collapse easily. Okay, so I don't worry about that because I'm in the modulationally stable regime, so I'm not worried about instabilities, and I expand according to this rule I have here, and use slow and fast, what we call multiple scales, slow and fast variables, okay, under this rule for capital T, capital X, and capital Y, capital T, capital R, capital theta for the cylindrical geometry, okay? And more or less, this is it. You're done. You're done. If you have this, you're done because you go back, you substitute to the equations, and you start separating orders of approximation, essentially orders of epsilon. And what you find is, let me go back a bit. Okay, remember now I'm in capital phi. So phi small is my original variable. I'm in capital phi now. Rho 1 and rho 2 is what I'm interested in. Eta 1 and eta 2 are what I'm interested in. Okay, so I've expanded and substituted. So if you go back, you find the equations for phi. Guess what? This is here a Boussinesq equation. So that's the intermediate part of the system. Again, what I have with the tilde here is nothing more than the Cartesian or the Laplacian, the Laplacian in Cartesian or cylindrical geometries. Okay, this is not affected. Choose your geometry. These are the equations you're going to find. And you are also introducing two new parameters, which is the speed here, the speed in which the waves propagate. Normally, they call this speed of sound. Okay, if you're interested in NLS dynamics, this is the speed of sound, but it doesn't matter. We don't care about that, how you call it, I mean. And this is what now everything you need to pay attention in that parameter alpha here. Okay, that alpha depends on the background on your continuous wave solution and the non-local parameter. And of course, now alpha can be positive or negative. And it can be positive or negative in two ways, which is surprising, in two ways. If you're given an intensity, a U naught, okay, by the experiment to be specific, then you can adjust your non-locality D in order for alpha to be negative or positive. And if you're given a specific non-locality D, you can adjust the background for alpha to be negative or positive. Either way, alpha has a sign. This is crucial now. So alpha can be allowed to have a sign. So we've derived the Boussinesq equation, and then you do the long time asymptotics as you would do in shallow water, let's just say. Okay, you go from the Boussinesq to the KP system. How? You expand phi, and you define another set of scales. Now, you're not obligated to do this. You can go from start. Okay, you can ignore the intermediate step. I don't think you should, because the Boussinesq system is very interesting by itself, but you can ignore it. Remember, capital X, capital T are all already defined in the intermediate dynamics. You can ignore that and have them, if you substitute the true form here, it would still work, ignoring the intermediate dynamics. I don't think you should, but you can do this, okay? So it seems that you're introducing even newer variables, but you're not. Essentially, you're not. You can still go back to the original system. And if you do that, you substitute, you get, of course, let me go back to the Boussinesq, you see you have a second derivative in time, Okay, so to first order to zero order, this is the wave equation. Okay, so you have a wave propagating on the left and a wave propagating on the right. Exactly what you're getting here: a wave propagating on the left and a wave propagating on the right. Okay, you substitute back to the system, and we've all done this before. You ignore or you set secular terms to zero. Okay, you don't want circularities, you don't want bad behaviors, and if this is the same slide. That's why I'm not paying any extra attention. This slide is the same as this one: Cartesian geometry and cylindrical geometry. There's nothing more to say other than the operators will change because of the geometry, but the ideas are exactly the same. I'm not doing anything more than just changing the operators to adjust to the different geometries. And if you do that, what happens? Well, you get KP system. Well, now you get the KP system, but you also have that alpha here. Remember that alpha? This has a sign now. Okay, this has a sign. This is the KP, and it has a sign. KP in Cartesian, KP in cylindrical geometry. In cylindrical geometry, this is often called the Johnson's equation. He was the first to derive the analogous of KP for cylindrical geometry. And now, because of the sign that you get from alpha, you can have alpha to be positive or negative. And if you go back to the theory of shallow water, this corresponds, the sign of alpha corresponds to what we will be calling the surface tension, high surface tension, small surface tension in the context of shallow water, which I'll show you in a bit. But in our case, because it's related to the non-local parameter of the original system, if D is bigger than a quarter of U naught squared, we call this the strong non-locality case or the weak non-locality case. So alpha can be negative or positive, and that will fundamentally change the system that you're studying. In what sense? Here, I haven't done anything other than renormalize, because look, this is a horrible equation, okay? We don't like horrible equations. We want equations with the fewer coefficients, the better. And this is what I've done here. I just removed the coefficients. So I moved the sign I was telling you about, I moved it to sigma. So this is of course the KdV, first derivative of the KdV plus uyy. The same is the same for the Johnson's equation. Okay. Now, sigma is important in the theory of shallow water because it tells you that parameter is small surface tension sigma is 1, okay, or large surface tension if sigma squared is -1. Well, how is that affecting you? It is affecting you in a profound change. Why? If the sign here changes, then you are referring to the KP2, Kadomchev-Petyashvili 2 KP2 system or the KP1 system, where these two have completely different solutions. Forget the properties. They also have different properties, but forget the properties for now. They have different solutions, very different solutions. Okay, depending on the sign of sigma squared, you have way different solutions. So that's important. You have to be careful. What do we mean by surface tension? Let me move. There we are. So what's surface tension? Well, I love these pictures because you're seeing here something that should not exist, but it does because of surface tension. Is what a surface tension is in fluids is read the red. It says it's the property of the liquid that makes it acquire the least surface area possible. This is, to me, it's we all know it. If you've ever studied physics, you know that nature is, of course, very lazy. Doesn't want to spend any energy. Okay, and I can relate to that because I'm also the same way. But it also wants to, for any liquid, it wants it to acquire the least surface area possible, which makes it form this very interesting, this very so insects can walk on water. They can form bubbles of water on top of water. It's very interesting to me. Well, how does that translate to our problem? Okay, I have here two tubes of water and mercury. Okay, see what's the difference? The difference between a surface of water and a surface of mercury is that water likes to make friends. The molecules of water prefer the molecules of the glass more than itself. So they stick, you see, they stick to the molecule, to the glass. However, mercury is not as friendly. Mercury prefers itself. It doesn't want to stick to the bottle, to the glass, I'm sorry, to the glass. So this phenomenon calls a meniscus. It's a beautiful Greek word, of course. It's a meniscus. So you have the concave up meniscus, concave meniscus, okay, for water. So you have a parabola, okay, for water, and for mercury, you have a convex meniscus, which is an upside parabola, okay? So that's the difference between what surface tension is. Small surface tension is a concave meniscus, okay? So small surface tension, for our case, you have to have water. If you want to see what I'm showing you now, in water, you have to have a concave meniscus, which means it's a small surface tension. Well, then you have to have water. If you want to have a convex meniscus, which is large surface tension, you have to go to mercury. Any experiments you're gonna make, depending on the behavior of KP1 or KP2, will be affected by the liquid you're using. So if you're using water, you're talking about small surface tension. If you're using mercury, I highly advise you not to mess with mercury because it's highly poisonous. Okay, then you have a large surface tension. Okay, so this is how this affects surface tension, affects the equation itself through surface tension. The material, the liquid you're using is going to affect the solution, or in a sense, the equation that you will be using. Okay, so let's go back. Now I'm using the solutions of the KP equations. Okay, I'm using the solutions of the KP equations, top and bottom, the KP equations, because I can find them, I know them. And the first one I'm going to use is the simplest one. Which one? The one that doesn't depend on y. Well, if your solution doesn't depend on y, then you simply have a KdV soliton. It's a KdV soliton. Okay, it's a symmetric soliton. Oops, there. And this is what you're seeing here. You're seeing a KdV soliton propagating. These are initial conditions. On the left, you're seeing the Cartesian, and on the right, you're seeing the ring solitons, which are the cylindrical solitons. Okay. Now, pay attention to this. Oops, I'm missing an L. This is a soliton. It's not a soliton. It's a soliton. Strong locality. When you have alpha, that parameter I was telling you about, alpha is 0. You have KP2 and an anti-dark soliton. An anti-dark soliton is essentially this case here, in this case, these are the anti-dark. So you have the background, and on top you stick a bright soliton of the KP or the KDV. Okay, if you have a dark, that would have been in the bottom. Now, what's interesting here is that these solutions do not exist if you're not in the small amplitude approximation. This is very interesting to me, that you go to small amplitude and you're finding solutions of the original non-local NLS that do not exist. They're not there unless you go to small amplitude approximation. And you have 4 of them, of course, 2 for each geometry. You have a dark, okay, and an anti-dark solid. I thought it was very interesting. And then, of course, you propagate them. We numerically propagate those to see if what we found was indeed a soliton, meaning that you're finding solutions or stripes in this case. You see, there is no y dependence here. There is no y dependence. You're not expecting to see any y dependence, or you're not expecting to find any theta dependence, any angle dependence on the ring solids. So you're propagating, and what's important here is to test if the propagating, the velocity that they're propagating with is the same as the one you predicted. And of course it is. Okay, you have to check that the C that you found, the capital C that we found, is the same as the one we predicted from our theory. So numerically, this is to test 2 things. The stability that you actually found the soliton, which is of course y independent, and that it propagates under the properties that you have already predicted. So this is the easy case. And then you get a bit greedy and you say, well, now let's have some fun. And let's define fun here. Fun is the pictures I showed you in the beginning. You know that the KP, besides the striped solitons or the ring solitons, has many interesting solutions that even can be observed in shallow water. I'm showing you one right here. The left is, they call it the X-type interaction. So you have 2 line solitons of the KP and they're interacting. And you see they have a small lump in the middle. Okay, this is water, this is light. And you have more than one X-type interactions. You can a short stem and you have a long stem interaction. Okay, you see this is water, this is light. And you have H-type interactions or Y-type interactions. Okay, why not have them both in light? And we're mimicking here exactly what people have seen and found in water, so that it can be reproduced in light or in nematic liquid crystals or whenever this non-local model may apply. So to test what we found, the movies, I'm not very good at making movies in MATLAB. So, whoops, let me see if I can. The resolution is not that good. What you're about to see is the Y interaction. So I have here 2 line solitons of the KP, and these are evolving under the non-local NLS that I showed you in the beginning. And you see, of course, that Y formatting and propagating in the velocity that I mentioned before. Okay, so you're seeing, indeed, you're seeing a Y soliton or a Y-type interaction, if you call it, of the KP, but you're now seeing it in liquid crystals or wherever that model may be applied. And of course, we want to test the stability of this in cylindrical geometries. Unfortunately, if you know anything, especially Kenichi, that you're expert in the KP system, if you know any more interesting or more exotic solutions of the Johnson system or the KP in cylindrical geometry, I'll be very interested in reproducing them for our non-local NLS. So what we did for the ring solitons is we said, let's see if they have the soliton properties that we say they have. So we put a small one, you see A is the yellow one B is, let's say, the black one, and we're evolving those. Okay, we're evolving those. A is faster than B, so it's going to expand faster than B is expanding. Okay, they meet at some point, and then you see one passes through the other, and nothing happens. The same for anti-dark ring solitons. A propagates faster than B. Okay, they meet, nothing happens. A has expanded faster than B. Okay, so this is to test that you're indeed talking about bright solitons. You're talking about solitons that when they interact, they don't feel the presence of each other. Nothing happens essentially, and they propagate with a correct velocity. That's the way of us testing that these are indeed solitons and they behave as such even under the non-local NLS. Now you get greedy and say, look, you go to light, you have different frequencies. You can, in any case, you can make things worse. In what sense? You can have coupled systems, much like we have the coupled NLS, where you have different solutions depending on the system, if it's focusing, defocusing, focusing, and defocusing. And you have a plethora of soliton pairs, we call them. Let's see if we can get these soliton pairs for the non-local system here. And indeed we did. We got, we call them coupled nematicons because we've used them under the context of nematic liquid crystals, but it doesn't matter. We get a dark-dark pair, dark-dark, anti-dark pair. These, again, these do not exist unless you go to the small amplitude approximation. Okay, so we have dark-dark, anti-dark pair. And look at this, a dark-bright pair, dark-bright. I thought it was very interesting. You get any combination you want to get, it's there. You can find all combinations of different solutions for the coupled system. Okay, and this is the papers that I was telling you about. The first one we did in optics letters. This was a more an optics paper in the sense that we did the cylindrical geometry. That's very interesting in optics. This is the cylindrical geometry, the first one. The second one is the mathy paper, if you will, that we did the expansions very rigorously, very carefully, even went to 3D. If you're interested in the full theory, this is the paper. The third one is the vector problem, the coupled equations, and the last one is the exotic solutions, so the solutions of the y's and the x's and the h that may appear in the non-local system. So with that, arigato, ευχαριστώ, thank you for the invitation. I know that this also says arigato. How do you pronounce it, that Kenichi? Arigato.
You are right. You're right. Perfect.
Okay. Perfect. Okay. So with that, I thank you. Thank you for your time. If you have any questions, I'm happy to answer any questions.
Thank you very much. Okay, so if you have a question, please. Okay, so please, yeah. There.
Yeah, Matteo, go ahead.
Yeah. Yes, yeah, Matteo.
Yeah. So I have two. Thank you, Theodoros. Always very interesting to listen to your work. So I have like two little questions. So one is about like a mere curiosity that I have. That is in your slide 3, I think, or something. One of the very beginning ones. And when you first introduce your system.
This one.
The one where the yes, this one. So clearly this one reduces to the NLS equation when d is equal to 0, and that is an integrable case. Like as an integrable person myself, and just as a mere curiosity, And I understand this is not deeply related with your investigation, which is independent from the integrable or non-integrable character of these equations. But so are there other known integrable cases for other specific choices of D, or is D equal to 0 the only integrable case?
That's the only integrable that we know of. You're absolutely correct. D0 is the only integrable one. You can find other solutions for the focusing problem. So if that was a plus here, I can tell you an exact solution that behaves as soliton, but you cannot prove that this is integrable. By no means, no, you cannot. In fact, people say it's not integrable. Okay.
Okay, so for a generic choice of D,
that something is not integrable.
I mean, it's hard.
No.
It's hard. I mean, the question is, for instance, if it passes the Panleve test or things like that, for instance, and I imagine that people have tried. So, I mean, this is interesting because, I mean, it looks like
it does pass the Panleve test because, and you can also find, a balance in the terms of this is a set-squared solution. Okay, so it passes the Panleve test in that sense, but I don't know. Let's just say it's not integrable. Now, what you're saying is very important. That if D is 0, yes, it is integrable, and you can follow through every bit of the analysis I presented to you. You can follow through with D equals 0 and find results for the NLS. So the D equals is included in our analysis.
Yes.
Okay, it's not a singular case. Every single bit is included in there.
Yes. Okay.
Okay. Did
Beautiful.
I answer
Nice.
the question? Is that?
Yes. Yeah, well, proving that something is non-integrable is always very hard. I mean, in fact, impossible. It's somehow, if something is integrable, you display. I mean, you show the Lax pair or an infinity, a hierarchy of conservation laws, and then you are done. Doing the opposite is very different. I understand. Thanks a lot. And one final question, if I can, is about, so again, it's my curiosity, is about how the numerical solutions that you displayed have been, particularly the numerical simulation that you displayed, how have they been made? So is this like yeah, please.
We use the algorithm by Kasam and Professor. EDD exponential time domain RK4. ETD RK4. It's by Kasam and Professor. It's spectrally in X, fourth order in time.
But it's like, it's a sort of method of lines where you transform your PDE in a ODE for all the points on the line, and then you integrate like with a Runge-Kutta in time, or it's like based on a different procedure? You're
essentially taking the Fourier transform of this one.
In space.
Okay. In space, and then you do Runge-Kutta. You're absolutely on the spectral domain. Yes. You're evolving it in Fourier space. Yes.
Because it's surprisingly numerically stable, and for a domain that is for a domain that is not completely periodic, because what you have shown is a numerical simulation where we don't have the periodicity at the boundaries.
Absolutely. Yeah. But you say I cheated, of course. You know me. I have to cheat.
Yeah. No, I mean, I was interested in the cheat.
Okay, so you've exposed me there, Matteo. Thank you for exposing me.
No, sorry, Theodoros. No, because recently I'm facing some problems, and that's why I'm asking, because I'm facing similar problems.
Canceling any back noise from the boundaries. I'm canceling any back noise from the boundaries. Okay, so that's it's not making it periodic, but it's not big enough to destroy the solution, the propagation of the solution.
Okay, so you have what, some absorbing conditions at the boundary that absorb?
Yeah. That's right. You got it. Yeah. Some absorbing boundaries. It's not easy because you have to have like a boundary layer it's an absorbing layer at the boundaries. Okay, but it's doable. It's doable.
Okay, yeah, then we may have a chat, because I would like to understand a little bit more about that. Thank you.
Sure.
So you are using windowing method, something around the boundary, you apply some filter.
Yes,
Okay.
that's right. That's right.
Yeah, so that
you have an absorbing field
yes.
from the,
Yeah,
boundaries. It's
you-
essentially making it periodic when it's not.
Yes.
Yeah. Okay.
Okay. So are there other questions?
Yes, thank you very much, Dr. Horikis. It's very
Thank
nice
you,
talking.
thank you.
And my
Thank you,
question is
Horikis.
about the physical meaning of the parameter D, a degree of
Mhm.
non-locality. It's in the case of water waves, as you explained, it's connected to the surface tension. How about the other system? For example, in the case of light, can you connect the meaning of this parameter D in the system of light? I mean, physical meaning of D in the system of light.
So when you're in light, so let's yes, yep. So when you're doing, say, in pneumatic liquid crystals, okay, it's the non-locality is it corresponds to the light what you call it my mind is stuck. I'm sorry. The way the material reacts to light. Okay. So that's the how do you call it? It's the response of the material to light.
Material. Okay.
That's the physical meaning, if you will. The way the material reacts to light. The way it wants to guide light within its molecules, basically. Okay, it's the correspondence to light.
And also, alpha can be negative or positive in the case of light. I mean,
absolutely.
Okay.
Of course.
So it ranges from small value to large.
Because you see, alpha. If you give me a D, let me show you again. If you give me your D. Find it. There you go. There. You see, if you give me D, then I can adjust. U naught is a free parameter. I can adjust how big my background is going to be so that I'm in the positive or negative regime. See, for a given D, if you're telling me, this is a pneumatic liquid crystal and D is 100. Because when you go to pneumatics, D is a big number, it's 100, 200, 500. Okay. Fine. I'm going to say, yeah, you want it that big, that's not a problem. Because I will adjust my free parameter, which is my background, I will adjust it so that one of these two inequalities is correct. Okay. And you can have it because U naught is a free parameter for you. Okay. So you can adjust in light, you can adjust the strong non-locality or weak non-locality regime as much as you like. Absolutely.
Okay, thank you very much.
Sure.
Are there any questions? Okay, so I have a question. So if D equals 0, then it's integrable NLS. So in this case, alpha is 1. Yeah. Alpha is 1, so positive.
1. Yep. Yes.
So weak non-linearity means in KP is KP1. Weak non-linearity, non-locality case is KP1. Yes. Yeah, KP1.
Yeah, you see, if you see there, right, you see,
yes,
is KP1.
KP1.
Okay, so NLS is what I didn't mention here is in KP in our case you solve these lines and everything, but if you go to the other case, then you see lumps, lump solutions, which of course Kenichi knows very well about. Lumps, however, have not been observed in shallow water. Okay, why? Because surface tension is your enemy there. You have to go do experiments with mercury, which is of course highly poisonous. You don't want to mess with mercury. Okay, there's no way you can make experiments with water and see these KP lumps. Okay, but if you go to our paper, the last paper I showed you here, oops, there, for PRL, this one, if you go to this paper, we also have the lump solutions of the KP. Okay.
Yeah. So, oh, sorry. So, yeah, if D equals 0, then this integrable NLS is defocusing. Defocusing NLS?
Defocusing NLS. Yes, defocusing. Yeah, which is if it was focusing, then you would have an unstable background and you wouldn't be able to support the solutions. It would be you know, modulationally unstable. So none of this would happen. Absolutely. Yeah. So that we cannot fix. We cannot fix the the sign of the system. We can only fix the non-locality. If you choose the system to be focusing, then none of this will work.
So focusing case, we cannot do this kind of things. Only defocusing case.
No, not in the small lump. Only defocus, absolutely, because it's the only case that you have with a stable background. Yes.
I see. Yeah, thank you very much. Yes. Yeah, very interesting. Yes.
Sure. Well, thank you.
Are there any questions? Okay, so let's thank to Theodoros. Thank you very much.
Okay. Thank you. It's a pleasure.